Okay, this is 4.6b, College Algebra. We're on example 2. We just did A in the last video and found out that our interest rate is 0.08. The B part of this says find the exponential growth function. So it wants us to find the equation. Alright, so what we're going to do is we're going to take this formula, we're going to plug 0.08 in for K, and 2,000 for this, because that's how much we had initially, and that's all we're going to do. So P of t equals the initial amount we invested, which they gave us, e to the 0.08 t. Okay, there's your formula for B. C says, what will the balance be after 10 years? Alright, so now we're going to take this formula here and we're going to determine how much money you're going to make in 10 years. So not only how much money you're going to make in interest, plus the amount you started with. So it's going to include both of those. So we're going to say how long? 10 years equals 2,000 e to the 0.08 times 10. Alright, so notice we are not going to have an exponent up here. That being the case, we're not going to use logarithms. So P of 10 equals 2,000 e to the 0.08 times 10 is 0.8. So you're going to take e to the 0.8 power, multiply it by 2,000, and you're going to get your answer. And in this case, in 10 years, you're going to have $4,451.08. You more than doubled the money that you invested in 10 years, and you didn't do anything. Alright, so let's go ahead and look at what they're asking us to do for part D. It says, after how long will the $2,000 have doubled? Okay, so this is the doubling part. We did doubling time on the population growth. The exact same thing here. We're going to use a capital T. And we're looking for the time that it's going to double. And we know it's going to be P of t is going to be 2 times our original investment, which is 2,000. Okay, so we've got that. So let's go ahead and replace P of t with 4,000 from here, and that equals what we started with, e to the 0.08 t. So again, the t is what we're looking for. We're all this stuff going together, we want to find out what t has to be to make this equal to 4,000. Alright, so again, we divide by 2,000, and you will always, 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 when you do this, get 2 because you doubled it. Okay, so then we get e to the 0.08 t. Capital T to remind you that you're doubling. Okay, not too bad. Now we take the ln of this, the ln of this, so the ln of 2 equals I'm going to just do all of the work here, t ln of 8, because remember this goes in front. This is equal to 1, so it can go away. And now you divide by 0.08. 0.08, those go away. So t equals the natural log of 2, and then you divide that by 0.08, and you get, for your doubling time, 8.7 years. So if you put that $2,000 in the bank, and you're like, okay, how many years is going to have to go by before that doubles? 8.7 years, and then it will have doubled in value. Okay, 3 more examples to go, and we're going to do example 3, world population growth. Alright, see right above example 3, there's a growth rate and doubling rate, and it says that the growth rate K and the doubling time T are related, and they give you some problems there. So those are some equations that we're going to end up using here. Alright, it says the population of the world is now doubling every 57.8 years. What is the exponential growth rate? So what we're looking for is K, the exponential growth rate. We want to find out the percent that the population grows each year. That's what the population growth rate is. All right, so I'm going to look at those three formulas up there in that blue box, growth rate and doubling rate, and I'm going to find the one that sets k equal to something because I'm looking for k. That's what they asked me to do. What is the exponential growth rate? So the formula that has k in it is this one, where k equals. So let's see what they've given us. We have two variables. We have a k and we have a t. We're looking for k, so they should have given us t so that we can solve this. So k equals ln of 2, and what is t? Capital T, so that's a doubling, 57.8. So you take your calculator, find ln of 2, and then divide that by 57.8, and that gives you a number close to 1.2%. And that's it. All right, models of limited growth. Let's look and see what that is. I pushed the wrong button. I thought I lost you there. All right, models of limited growth. The model, P of t, equals your initial p, e to the kt power, where k is greater than 0, has many applications involving unlimited population growth. However, in some populations, there can be factors that prevent a population from exceeding some limiting value. Perhaps a limitation on food, living space, or other natural resources. Okay, so what they're saying here is, well, let's look at example 4, and you'll get what I mean when I say a limited growth. Okay, a ship carrying 1,000 passengers has a misfortune to be shipwrecked on a small island from which the passengers are never rescued. So you got 1,000 people there. The natural resources of the island limit the population to 5,780, which means once there's that many people there, there won't be any more because they will die somehow to keep that population the same because the island can't sustain more than that. So they will starve to death, or maybe there'll be people that may drown while they're out fishing, or die of old age, or die of sickness, or that kind of thing. But the maximum population that island can provide food for is 5,780. Okay, so the population gets closer and closer to this limiting value, but never reaches it. The population of the island after time t in years, so after a certain amount of time in years, is given by the function, and then they give you your population given a certain amount of time equals 5,780, so they give you the formula here, over 1 plus 4.78 e to the negative 0.4 t. There's the formula for this particular problem. Now if you look on the bottom of page 414, they give you the same equation, but they have an a up here, and they have a b here, and a k here. Okay, so sometimes you're going to have to find what those are, but this particular problem, example 4, they give you that formula. Okay, so the graph of P of t, which is this one here, is a curve shown at the left in your book, and I don't really care about the rest of it there. Using a calculator, we compute the function values. We find that in year 0, they just get shipwrecked. There's 1,000 people there. Okay? What happens after, let's say, 10 years? So in 10 years, then it's going to be multiplied by 10 there. Then you can figure out what the population will be in 10 years. And when you do that, you'll get 5,314.7. So notice that this number now, as time is going by, it went from 1,000 to, in 10 years, 5,314. So population has grown quite significantly in 10 years. Lots of people having babies. All right, so we said that it can only hold 5,780. So as this number here gets larger and larger, this number here gets closer and closer to the 5,780 maximum population. The thing to remember, though, is it will never get there. I mean, for instance, if I put p to the 1,000 and said, in 1,000 years, what will that population be? Well, it might be 5,779.888. Okay, so it might be awful close to 5,780, but it will never get there. It will get closer and closer and closer, but these decimals will never round out to be exactly 5,780. Okay, so one of the things about limiting population or limiting growth, it will never quite get there. Okay, so let's look at, what do we have? One more, and this is called exponential decay. And obviously I do not believe in evolution. I do not believe in carbon 14 dating and that all works, but those are a couple problems that they have here. And when they're talking about exponential decay, they're again using this formula. And notice, this k is a negative. Okay, I think on all the other ones, the k was a positive, but in exponential decay, it's a negative. So, half-life. Half-life of something is how fast it decays. So what happens is, if I say that the half-life of boron is 1,000 years, that means in 1,000 years it will decay in half. Okay, so when I use the word half-life, I'm saying in a certain amount of time, for each particular element or whatever we're looking at, in a certain amount of time, it will have half of it left. It will have decayed half. All right, so let's look at carbon dating and see if we can do this when I have less than 3 minutes. So I don't know if I'm going to do that or not. Let's go ahead and put it on the next video, and it'll just be a couple minutes long, but I don't want to run out of time.